Minimize, pull that back up. Okay, all right. Lecture 11. Let's get started. A couple quick announcements. I actually got more emails about homework 2.7 than I have probably any other assignment. I hope I got to all of them. I think probably the hardest part about that assignment was the very first step. Once you get the AB, the AC, and the AD, the rest is very rote. I know I do also still have a couple of emails here and there that I'm still catching up on from students, and so my goal is to try and catch up on everything throughout the weekend and whatnot. But a little bit on housekeeping. So I believe homeworks 2.3 through 2.5 are now graded. 2.6 is still being graded. I checked that last night and it was still being graded, although it looked like most of it had been taken care of. I'm not sure if it got finished this morning. 2.7 is due today, and that is the last homework that covers exam 1. Okay. Now I'm assigning a homework today on the topic that we're discussing today, which is cross products, but it's not due until next Friday. So today we're going to discuss cross products, and then Monday we're going to have our exam review. Wednesday we're going to celebrate, and then Friday we will come back and get back into the land of exam 2, where in Friday we formally introduce the concept of a moment. So coming back next Friday, homework 3.1 will be due. Now, given the fact that this homework bridges an incoming celebration, I will tell you that this homework is very short, at least in comparison to the last one you just submitted. The last one, I think, is much longer than this one. This one will take you a matter of minutes, because it's just giving you a couple of vectors and evaluating the cross products, doing it 2 different ways. So it's very, very straightforward. Any questions on housekeeping so far? Okay. One thing I did want to mention, and I wanted to go ahead and plant this seed in your head now, is, like I said, we do have a celebration coming up, and I wanted to mention something now in case you wanted to go ahead and get started on developing a formula sheet. Let's talk about that. So my exams are closed book and closed notes, but I do allow you to generate a formula sheet. Okay, you can put whatever you want on the formula sheet, but I do have the following stipulations. I'm going to collect them after the exam, but I just want to make sure you're aware of 3 things. So just make sure you have your name on it. First off, it's 8.5 by 11. It's front and back. You can put whatever you want on it. Okay, except for I don't want you to include any fully worked out example problems. That's not for my benefit, more so that it is for yours. Because what will end up happening is you'll be working an exam problem, and then you'll have an example problem on your formula sheet, and I've seen it where students pull values from the problem on their formula sheet, and they get intertwined in the exam problem, and suddenly they're doing their exam problem, and there's values that came out of nowhere, and it actually makes it more difficult. Whereas if you just synthesize the processes and the formulas and whatnot on the formula sheet, it actually ends up working out better. But my final stipulation is I do want the formula sheet to be prepared by you. And what I mean by that is I'm fine if you handwrite it. I'm fine if you word process it. I'm even fine if you screenshot an image here and there from the PowerPoints. But what I don't want to see is just take all the slides, put them on a sheet, and hit print, because I actually think you need to go through the process of making it, okay? I have found that actually going through the process of making the formula sheet, that is studying, okay? And I'll tell you that you won't be surprised. I'll be surprised at how many people are taking the exam and don't even look at it, because by making the formula sheet, they went through the process of organizing their thoughts. And I think you'll find, or have found up until now, there aren't exactly a lot of formulas in this class. I mean, there are processes and procedures, but there aren't a whole lot of equations to memorize. This isn't like physics or, deformables, which you'll take later, where there's just oodles and noodles of formulas. Okay, any questions? All right, so let's get into the land of cross products. And I want to set the stage a little bit for today's lecture. I'm going to go ahead and tell you that today's lecture is going to be very mathy, okay? It's going to be kind of very derivation intense and whatnot. But I want to explain what's going on here. So I would argue that the first unit of this class is really centered around one concept, and that's adding vectors, okay? Now there was a physical connotation to that, and that's that, we've got the scenario of a series of forces all meeting to a common point. And so we can apply principles of static equilibrium, determine what are the necessary unknown forces to keep that particle in equilibrium, and so on and so forth. But mathematically, we were talking about adding vectors. And not only were there sort of numerical mathematical principles, we can take that vector and we can split it up into IJK format and then add up all the I components, add up all the J components, add up all the K components. But there was also a geometric representation to it, a graphical representation. We had vectors represented as these arrows in space, and addition of vectors is just taking those vectors in a tip-to-tail fashion. So the resultant is from the beginning to the end. And we found, based on that graphical representation, that it didn't matter what order that you added vectors in, that A plus B equals B plus A, and there were other just various aspects that we saw with vector addition. You could take a vector and multiply it by a number. It wouldn't change its orientation, but it would change its magnitude, stuff like that. Now what I want to do is I want to introduce the concept of multiplying vectors. So I want to take vector A and vector B and multiply them, okay? And I argue that what we need to do first off in order to figure out how to do that is sort of define what are our goals for vector multiplication, what are we trying to achieve, what's the product going to be, and so on and so forth. And so we're going to start with the concept of a cross product. Now, I imagine that some of you have heard of cross products before. I think I asked this, and some of you would raise your hand. And I think there's some of you that probably have not heard of cross products before. So I've sort of designed this lecture so that if you've heard it before, maybe this is a little boring. If you haven't heard it before, it should be right on pace. But hopefully, by the time that we're done with this lecture, everybody will kind of get the general idea of what it means to compute a cross product. So, like I said, we've learned how to add vectors. Now I want to learn how to, I want to discuss how to multiply vectors. And I want to explain, first off, why. The reason why we are learning how to multiply vectors is because the multiplication of vectors is how we are going to assess rigid body systems. And all rigid body systems is trying to explain is what happens when all the forces don't meet at a common point. Okay? And the way that we handle that is we have to introduce a new concept, and that's the definition of a moment. Okay? And so moments are going to be the star of the show for exam 2. Now, if I have vector A and vector B, there are two ways that I could multiply them. I could take vector A, vector B, and multiply them and get a scalar, or I could take vector A and vector B, multiply them, and get another vector, okay? And so we can, mathematicians will call those maybe the scalar product or the vector product, but because of the notation that we use as mathematicians and engineers, we tend to colloquially refer to those as dot products and cross products. So if you've had experience with dot products and cross products before, you probably know what I'm talking about. That if you take a vector, if you take two vectors, A and B, and you dot them, you get a number. But if you take vector A and vector B and you cross them, you get another vector, okay? Now, what we're going to find in this course, well, let me say this generally. Each of these products has specific goals, specific applications. What we're going to find is that vector products or cross products are going to be more inherently useful to us. We are going to find that we have a use for vector products far more than we do scalar products. That's why we're starting with cross products. I'd also argue for anybody that has any experience with this, vector products are maybe a little bit more difficult. Dot products are simple. The actual mechanics of computing a dot product, you just take each of the components or the constant coefficients, multiply those together and add them. But with vector products or cross products, there's a little bit more to it. Okay? Now, before we start going through the formula or determining how to define the cross product or how to compute the cross product, I think what we should do is define what the cross product should represent. Okay? What I mean by that is this. Okay, so let's say I have vector A and vector B, and I want to multiply them to obtain a new vector. We'll call it vector C. So what are the properties of vector C? What are the things I need to define? I need to know, well, what do all vectors contain? They contain a magnitude and a direction, right? So I want to know what are the magnitude and direction of this cross product, this C vector. And I think more specifically, I want to define this in such a way that the operation is, I guess, one-to-one. And what I mean by that is I want to take vector A and vector B and cross them and get a predictable result every time. It's like numerical multiplication. If I take 2 times 3, I get 6, okay? I don't want to repeat that operation 2 times 3 and get maybe 7, right? I want a single answer every time I do a cross product. So I need a magnitude and I need a direction, okay? So let's start off by trying to visualize that. I found a little widget online that does this a heck of a lot better than I could graphically, okay? So this is a graphic that shows what happens when you take vector A and vector B and you cross them, okay? So what I've got are 2 arbitrary vectors in space. So we'll call it vector A and vector B. Now, vector A and vector B could be, on the plane this way, they could be pointing this way, what have you. But 2 vectors just pointing at a random direction in space. Now, geometry tells me that what I can do for these vectors is define a plane that these 2 vectors sit on. Now, right here, I've got this on the XY plane, but I could rotate this coordinate system. Let me get this rotated. I could rotate this really sort of in any direction, and no matter which way these 2 vectors are facing, there is a single unique plane that is formed by these vectors. Okay, so that's pretty useful, okay? So what I can do is I can say, I tell you what, let's look at this from a magnitude and direction standpoint. So I propose that we can define the cross product such that the magnitude or the length of this new vector is equal to the area of this parallelogram. And that's really valuable because if I take these vectors and I start changing, their magnitude or whatnot, suddenly the resulting magnitude of the cross product changes. If I take this one vector and I make it longer, now the cross product gets bigger. If I take it and make it shorter, now the cross product gets smaller. But now I have a way of defining the magnitude such that it's predictable. Regardless of what vector A and what vector B are, if I plug them in, I get a new result and its magnitude is predictable. What about its direction? Okay, like I said, vector A and vector B, there exists a plane that is formed that both of those vectors lie on. So I propose that I can define the direction of that vector normal to that plane. And normal just means that if you've never heard that term, normal just means that it's perpendicular everywhere on the plane. So for example, if this table over here is a plane, then this marker right now would be normal to the plane because everywhere I look, it's at a right angle. So that's what the term normal means. So I have a unique magnitude and a unique direction. Now, I say unique direction maybe with a little asterisk because I propose that there are actually 2 directions normal to the plane. One direction is pointing up and the other direction is pointing down. Both of those vectors are normal to the plane. And what that's going to mean for cross products is that while we have a unique process defined, one of the things that we are going to lose is commutativity. And what that means is A cross B is not going to equal B cross A. In fact, they're going to be opposites of one another. If you flip the direction of cross products, you're going A cross B and B cross A. If you flip the terms, you're going to flip the direction of that normal vector. So for example, this is A cross B, that is B cross A. So does that graphically or geometrically make sense? Okay, I'm not sure if that's ever been shown to you in that way, but I found that pretty valuable when I was surfing for tools and whatnot. Okay, so if I look at this mathematically, so we're going to define the cross product so that the direction points in, the direction is perpendicular or normal to the plane formed by the 2 vectors, and the magnitude is the area of this parallelogram. And if I break out my geometry, my high school geometry, I can compute the area of this parallelogram as the magnitude of this, and then the sine of this angle. That's actually going to be kind of important because one challenge that we might ask is if we have these 2 random vectors out in space, what's the angle between them? We can use the cross product to do that. We can actually use the dot product to do that as well. I would argue the dot product's maybe a little easier, but we'll get to that later. Okay. Now, like I said, one of the things that we are going to lose with cross products is the concept of commutativity. Okay, so let's get into how we actually go about defining our directions And what we do is, like I said, so the cross product will be normal to that plane. The way that we define that direction is we use what's called the right-hand rule. And so this is our mathematical, this is shorthand for the mathematical convention that we use to define positive directions in 3D. So the way that works is, so let's say I have vector A and vector B. The reason that we call it the right-hand rule is we take our right hand open and we point it towards the first vector, and then we take our fingers and we curl them towards the second vector. So A cross B indicates the cross product points up. That's where our thumb, that's where the right-hand rule goes. So A cross B goes like this. Whereas if you do it in the opposite direction, you do B cross A, the only way to get your hand to work that way is if you have B cross A, hence why your thumb points down. So this is what I meant when I say that we sort of lose commutativity. Remember what happened in when we first started learning about vectors. If I take a vector and multiply it by -1, what does it do? It doesn't change its magnitude, but it flips its direction, okay? Well, if cross products flip the direction, so what that means is that A cross B equals the opposite or the negative of B cross A. So cross products are not commutative, okay? Does that make sense? Okay, this is great on concept, but we need to start learning how to actually compute these things. Like, this is great, this is an idea, okay? I need to know how to do it. How do I actually compute a cross product, okay? So I have found that the easiest way to explain how to compute a cross product is to look at the simplest vectors. And the simplest vectors are I, J, K, okay? So I'd like to look at this box here on the bottom because I kind of want to pay attention to this for a second. So each vector has a magnitude of 1, right? The I vector, the J vector, the K vector all have a length of 1. Now, what is the angle between these vectors? Like, what's the angle between I and K? 90 degrees, right? What's the angle between I and J? That's a 90-degree angle. The angle between each of these respective vectors is 90 degrees. So let's talk about magnitude. If I were to cross any one of these vectors, let's take I cross J. If I were to cross I and J, I would be looking at this parallelogram. What would the area of that parallelogram be? It'd be 1, right? Because it would just be a square, right? It would be a square that's 1 by 1. So if I cross any one of these two vectors that are opposite one another, so for example, if I cross J has a magnitude of 1. So let's look at I cross J. So I cross J has a magnitude of 1. What about its direction? Okay, so right-hand rule. I point towards I curl towards J. K goes like, the resulting vector it goes like this, which is actually in the direction of the K vector, right? So if this is the x-axis, curl towards the y-axis, my thumb points towards the z-axis. So let's think about that for a second. So if I'm crossing I and J, I know the magnitude is 1, and I know the vector points towards the z-axis. So what is the name of the vector that points towards the z-axis, points in the positive direction of the z-axis, and has a magnitude of 1? It's K, right? So what is I cross J? It is K. Does that make sense? So those fundamental definitions are what we can use. So the idea is that if I understand how to cross these basic vectors, I can cross any vector, okay? So, and I can keep going along with this. I can follow these similar patterns. So, for example, if I cross J and K, so point my hand towards J, curl towards K, I is going to go this way. So J cross K equals I, and K cross I equals J. So that's these, okay? I also know that if I were to flip these directions, so if I have I cross J equals K, I flip, I change the sign. Flip, change the sign. Flip, change the sign. Does that make sense? Yes?
Go back to the one where you guys hold it real quick.
I'm sorry, could you say it again?
Could you go back to the slide where you guys hold it real quick?
This one?
Yes. Thank you.
Sure, yeah.
On that slide that you were just on at the bottom, was that a 0? Like at the end?
At the very end, yes, I'm going to get to that here in a second. You were 100% right. I'm going to get to that here in a second. No problem. Did you get this?
Yeah.
All right. Everybody else good? Okay, so let's go to that. Okay. Now, one of the things I didn't look at is what happens if you cross a vector with itself. Okay, so let's think about that. What happens if I cross I with I? Well, magnitude and direction. What would be the size of that parallelogram formed if you crossed a vector with itself? It'd be 0, right? There is no area. It's not like crossing I and J where you have like a region. Okay, that region, it has an area of 1. If you cross a vector with itself, it has no magnitude. Right? So I propose if you cross I with itself, or J with itself, or K with itself, you get 0. Okay? Does that make sense? Okay, so we've got some pretty fundamental definitions here. We know the patterns for I and J and K. We also know what's crossed with themselves. I'm going to show you a really easy way of memorizing these here in a second. In fact, it's right here. So the way that I kind of do this is I go IJK and I sort of draw a circle, and I'm going to show you how to do this here in a second. But basically, going in one direction, the cross products are positive, and going in the other direction, they're negative. So like, for example, if I have I cross J, that equals K, and that's positive. J cross K, that equals I, that's positive. K cross I, that equals J, that's positive. If you go in the other direction, it's negative. So sort of a simple shorthand way of remembering that. Okay, now we know what the goals of the cross product are, so let's be clear about that. We know that A cross B needs to point in the direction normal of the plane. We know that the magnitude is equal to that parallelogram. But how do we compute it? Well, the answer is to use what we have learned from I and J and K. So we know how to cross these base vectors. We can use this to develop a formula for crossing any vector. I mean, after all, any arbitrary vector, like 2i plus 3j minus 4k, that's just a little bit of I, a little bit of j, and a little bit of k. So if you understand how to cross those, theoretically, you should understand how to cross anything. Okay? Now, this derivation is kind of long. This is kind of nasty. So I'm going to do this off to the side. I think there's actually some value in doing it off to the side. I want to show you how this works, okay? Now, I want to be clear. I'm not going to make you all do something like this on an exam, but I'm about teaching you stuff, and I have found that it is easier to just kind of go through this together. So let's say that I have, let's call it vector P, which is this. Okay? And let's say that I have vector Q, which is this. Okay? So my goal is to determine P cross Q. Okay? So what I'm doing is I'm taking that crossed with that. Oh, sorry. Okay. Now, let's go back to some basic algebra here, because this is going to be kind of long here in a second, but let's say you had 2x times let's say you had this. How would you do that algebraically? How would you handle that? Well, you multiply that out if you wanted to expand it. And how do you do that? You take the 2x times this term, the 2x times this term, the 2x times that term, right? You just do each one at a time. Well, we're going to do the same thing here. We're going to do each one at a time. So we've got 3 terms here and 3 terms here. So we're ultimately going to have 9 terms that we're going to be adding together. So let's carry this out. I know it's going to be kind of long, but I think it's kind of valuable to just go through it. So therefore, P cross Q is, okay, so let's handle the first term. So we have PX and QX. So what I'm doing, so that you're aware, so that you're following along what I'm doing, I'm taking this term times this term, then I'm going to take this term times that term, then I'm going to take this term times that term. Then I'm going to do the same thing with the second one. This one times this one times this, or sorry, whoop, I did that backwards. This one times this one, and this one times that one. And then I'm just going to keep on going. Does that make sense? All right. All right. So we have PX and QX. Remember, the way we define vectors, those are just numbers. So I'm going to stick them out on the side. And then I'm going to have I cross I plus PX QY I cross J plus PX QZ I cross K. And then go on with the next term. PY QX, and then we have J cross I. And again, notice how I'm keeping the order, right? So it's I cross J, I cross K, and then it's J cross I. That's going to be J cross J, J cross K. I'm keeping the order here. Is everybody kind of following along with what I'm doing here? Okay, because I didn't want to just say, oh, here it is on the slide, because on the slide it kind of looks like alphabet soup, but I wanted us to kind of evaluate it together. Okay, plus PZ, QX, K cross I, plus PZ, QY, K cross J, plus PZ, QZ, K cross K. The latent mathematician in me wants to say we just went through a series of permutations, every potential combination of these, or every potential iteration, all right? Okay. Does that make sense? Okay. Now, that's a lot. Can we simplify this a little bit? Let's start off with this. What is this? It's I cross I, and I cross I is 0, right? This is 0, that's 0, and that's 0, right? Anytime a vector is crossed with itself, it's 0. So we can get rid of that. We can get rid of that. We can get rid of that. Now, what about the others? Remember, I got like a simple way of remembering these cross products. So the way that I do that, this is how I do it. I say we have I, J, K. I draw a little circle around it, and I draw the circle in alphabetical order. So I sort of draw I, J, K like that. And I say that that's the positive direction. Okay? So what I mean by that is this. Okay? So if I have I cross J, what is I cross J? It's K, right? Okay. What about I cross K? What is I cross K? So I cross K is J, but is it positive or negative? Going in the opposite direction, it's negative. So maybe I'll say negative J. This right here, what's this term? What's J cross I? Say it again. negative k. What about j cross k? I. Oh, that's I. What about k cross I? I believe that's j. K cross j is negative I. Does that make sense? Questions? Okay, so what I can do is now I can start collecting all the terms that are common and write this as a vector. So what's the stuff times I plus what's the stuff times j plus what's the stuff times k. So let's deal with the I vector. So the I vector, let's see. We've got that and that. This is positive and this is negative. So maybe PYQZ minus PZQY. Did I do that right? Looks like I did. What about the J vector? The J vector is over here on the outskirts. We got PXQZ, PZQX, and this one's negative. Or right, no. This one's positive, that one's negative. So PZQX minus PXQZ. And then finally, we have PXQY negative PYQX. And I would argue this is the formula for the cross product. And make no mistake, that is the formula for the cross product. Whether you remember doing it this way, and I would bet most don't remember doing it this way, that's the formula. And all it is taking the observations that we know about the cross product, all it is taking those observations and extending them to any random arbitrary vector. The observations we know about ijk, just extending it to anything. So just so you're aware, let me show you something. So everything you see here on this is right here, okay? So this is what I had here on this slide. I just took it and I thought it was better to write it out. I know that might have seemed a little redundant, but I think it's easier to take this and write it out to actually understand it. Does that make sense? So here's what we've got here. This is a pretty big formula. I don't know about you, but I don't like remembering formulas. It's hard. I think it's easier to remember patterns, okay? So there's got to be a way to simplify this, right? The answer is yes, okay? And we actually turn again to matrix algebra, okay? In matrix algebra, one of the most important properties in characterizing a matrix is what is called the determinant, okay? And the determinant is basically, I'm trying to not get too far into linear algebra land, but it's sort of a summation of the independent products of terms and rows and columns in a matrix. And so I think I've talked about this before, but there's an entire class of math called linear algebra that its whole focus is to solve systems of equations. And one of the ways that you can characterize systems of equations is with the determinant. So for example, if the determinant is 0, then the system doesn't have a solution and what have you. This formula, I can take this formula and reorganize it as a determinant, and if I compute the determinant of this 3x3 matrix, the formula, the method that you use to compute the determinant is actually the same thing as what would be yielded by this equation. And if I was a betting man, this is what you all remember that have done the cross product before, am I right? You've probably done this before, okay? So if you expand this determinant, you will find that expanding this determinant equals this. But then again, it's probably been a while since you've done a determinant, right? So that's kind of what we're going to be doing today, all right? So I think that for 3x3s, there are two ways to solve a determinant. Okay, and I'm curious which one that you've done. Okay, so the first rule is what's called the rule of Saris. So the rule of Saris, what you do is if you have a 3x3 determinant, what you do is you rewrite the first two columns over here, and then you take all your products this way and they're positive. Then you take all your products this way that are negative, and you just add them all up. Is that the method that you all did before? Curious if anybody did that. Some of you probably did that, and I'm guessing that some of you probably did this, the one on the bottom. Yes? You did the one on the bottom. Yeah, so the one on the bottom is called cofactor expansion. So the one on the bottom is you basically expand across the first row. You take this term, knock out the rows and columns, and take the determinant of this, and then subtract this term, knock out the rows and columns, and take the determinant of that. And then this term, knock out the rows and columns, and take the determinant of this. How many did it the first way? I'm just curious. How many did it the second way? Okay, good. I actually prefer the second way. I think that when you first start teaching students, I think they kind of like the first way because it's a lot more visual. Personally, though, I like the second way because it's easier to group the I, J, and K terms together. So you can do whichever one you want. And by the way, to determine each of these 2x2 determinants, you just take this times this minus this times this. And think about it. This times this minus this times this. Doesn't that pattern kind of follow with this? This times this minus this times this. See how the pattern kind of follows along? So it's just a simple way of remembering the formula. Okay. What I want to do is I want to go through a cross-product example with you, and we're going to do this using both approaches, both the rule of Saris and cofactor expansion. This is meant to sort of unify the different methods that you all have used to compute cross-products in the past, so that when we're all said and done, we're comfortable with both ways. We have a way of checking our work, and in the end, we should be getting the same answer. Okay. So we got two vectors here. We've got A, which is 2i plus j plus k. Then we have B, which is negative 4i plus 3j plus k. And what we're going to do is we're going to compute the cross product using two different ways. The Casio will actually do this for you. This is one of the areas where I don't want to say I recommend against it, but it's actually kind of laborious to do it. And sometimes I think it's easier to just do it by hand. It'll do it. And I think I have a video that I recorded either last year or the year before that shows you how to do it. I might post that to the playlist. Okay. So let's go through this. Okay. Now, ultimately, what we're going to be doing is A cross B, and regardless of which method, what you're going to be doing is evaluating the determinant of this matrix. 2, 1, 1, negative 4, 3, 1. And if you're wondering where I got this, all I did is I took, 2, 1, 1, negative 4, 3, 1. I took either approach. Not either approach. I took each of these coefficients, just 2, 1, 1, negative 4, 3, 1. Now I'm going to go through and use either approach. Okay? So, now, let's start off with the rule of Saris. How many of you have heard it that way before, those of you, or heard that term, those of you that did it this way? Okay, cool, we've got, yes, somebody's got the terminology, I like it. So the way the rule of Saris works is we take I, 2 minus 4, J, 1, 3, K, 1, 1. And what we do is we rewrite the first two columns next to it. So we say I, 2, negative 4, J, 1, 3. Okay? And what we do is we take all of the products this way, we treat those as positive. Okay? So I'll use a red mark or red line for that. So we do that, that, that. So sort of diagonally. And we treat those as positive. So what do we get? Okay, we get the first one is I times 1, which is I. Then we have j times 1 times negative 4, right? So that's minus 4j. And then 2 times 3 times k, that's 6k. We group all of these. Then we do it again the other way, okay? So the other way, we go like that. Okay? And so the other way, what do we got? Well, we can do it in order, but I'm going to try and keep it with alphabetically. I'm going to do it, IJK. So the I term, we have I times 1 times 3. So we have 3I. We have j, which is 2 times 1 times j, so 2j. And then k is minus 4k. Now, the blue terms, we treat those as negative, okay? And the way that we do that is we just subtract all of that. So this quantity minus this quantity. And so all we do now is we just distribute our signs. So we have I minus 4j plus 6k minus 3I minus 2j and then plus 4k. Oh, forgot my hat there. All right, so you see why I did the plus 4? Because negative and negative is a positive, right? And so now all we do is collect our like terms. So i's, we have negative 2. J's, we have negative 6. K's, we have positive 10. So A cross B is that. Is that hard? Is everybody okay with that? So how many of you have never seen that before? Wow, okay, that's pretty cool. You learned something. Okay. Now let's do it the other way. The other way is what's called cofactor expansion. Okay? And so both of these methods are sort of graphical, visual processes. Okay? So cofactor expansion. All right. So I'm going to scroll down a little bit if it's okay. All right. So the way that cofactor expansion works is we have I times a smaller determinant. We have minus j times a smaller determinant plus k times a smaller determinant. So in other words, we expand along one of the rows, in this case the first row. You can actually expand along any row, but because of our notation, we tend to expand along the first row. And then we alternate our signs, so plus, minus, plus, plus, minus, plus. And as for figuring out what goes into these determinants, what we do is we cross out the rows and columns. So for I, we cross out the rows and columns associated with term I, and we're left with this block down here, this 1, 3, 1, 1. So 1, 3, 1, 1. For J, we cross out the rows and columns associated with term J. kind of difficult when the projector's just projecting right over my hand or my arms. But I've got 2 and -4, 1 and 1. And then K, we cross out the rows and columns associated with K, and we're left with 2, -4, 1, and 3. And this is a method I think a number of you have seen before. You've done it this way. Okay. All right. So equals, so how do we do the 2 by 2s? We just do that times this minus that times that. So what do we have here? This is 1, this is 3, so 1 minus 3 is -2. And then J, so let's look at J. What do we have here? Excuse me. 2, now pay attention to your signs. So this is 2, this is -4. So 2 minus -4. What's 2 minus -4? What's that? 6. But then there's also this negative here. So it's -6J. And then plus, so what about the K? So we have 2 times 3 is 6. This times this is -4. 6 minus -4 is 6 plus 4, or 10. By golly gosh gee, we got the same answer as we did before. Okay. So I'm curious, who prefers this rule of Saris? I'm just curious. Who prefers cofactor expansion? Okay, all right. You know, if you really want to learn about what drives an individual, ask them which method they prefer when they compute determinants. You know, none of the other stuff matters. All right, let me stop for a sec. Does anybody have any questions about this? Okay, now I want to be absolutely crystal clear. This is not on exam 1, okay? This is exam 2 material. You do have a homework, but it's due next Friday. I will say, though, this homework is really short. So if you wanted to knock it out, I mean, it wouldn't hurt my feelings at all. Monday, hold on, before we leave. Monday, we have exam review, okay? So what I'm going to do during exam review is I'm going to go through the general format of the exam, but I'm going to be, I'm not going to come in with 50 minutes prepared worth of material, because the purpose is for you to come in with your prepared questions. If you've got questions about stuff, concepts, be prepared to ask, okay? Chances are if you have a question, somebody else does too. Like somebody else has that same question, so be prepared. I'm going to pull up the code again. That's all I've got. We'll see you all on Monday. Oh, one other thing. If you happen to be in the engineering building around 10 a.m., it might be a little crowded due to the ceremony. Everybody's collecting over there, so just be aware of that. That's all I got. Have a wonderful weekend.